All right, moving on to section 8.2, transformations of logarithmic functions. And then you're going to get a little bit of deja vu here because we're going back to chapter 1 again. Yeah, this is getting real repetitive really quickly. So again, we'll ask the question, what does transformation does each variable do? So we have our A is our vertical stretch, K is our vertical translation, so up and down. B is our horizontal stretch, but again, when you say it, it's actually the reciprocal, so 1 over B, as well as when you apply it. And then H is going to be our horizontal translation. But this minus sign is part of the equation, so remember that. It's always going to be the opposite of what sign it is sitting there. And then we go and look, well, what transformation does each variable perform in a logarithmic function? Well, to no surprise, we have A is our vertical stretch. You can see it's sitting in the same location. K is our vertical translation, also sitting in the same location. B is also next to the X, and that's still going to be a horizontal stretch, and H is still our horizontal translation. So nothing has really changed so far, except for you can see the function notation has been replaced with a logarithmic notation, and we still have our base C here. So let's go back to some previous knowledge so we can kind of figure out how we would actually graph a logarithmic function. So we're going to graph f of x is equal to 2 to the power of x. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 squared is 4, and 2 cubed is 8. Going the other way then, 2 to the power of negative 1 is 1/2, 2 to the power of negative 2 is 1/4. I'm going to stop there. We have to make it very clear that this graph never actually hits the axis. There is an asymptote there. And then we're going to continue our graph. It's continuous in both directions. So there we go. We've got f of x is equal to 2 to the power of x. Now it's asking for us to draw the inverse. Now that inverse, that means we're reflecting over the line y equals x. And it also means that I'm going to switch the position so it's y comma k then. So here I have 0, 1. It's going to become 1, 0. Here I have 1, 2. It's going to become 2, 1. And we can see that this is an equal distance. If I was to draw a y equals x line here, this is just reflected over that line. And that's what we're looking for. So then I have 2, 4, which will become 4, 2. And then my final point that I have on the positive direction is 3, 8. Now that doesn't fit on my graph quite. So, well, here's got 8, 3, just barely. Now going the other direction, so this is negative 1, 1/2. So we're going to go to 1/2 then, and it'll be negative 1. And then negative 2, 1/4. So it's going to become 1/4, negative 2. And now we're going to have an asymptote actually on the y-axis then. And so it's a continuous graph. And again, make sure it doesn't look like it actually is going to cross this axis. And we should label that. So that's our inverse graph. Okay, our final step then. So show algebraically that the inverse of f of x is equal to 2 to the power of x is f of inverse of x is equal to the log base 2 of x. All right. So when we're taking this inverse, that means we're going to swap the positions of these two variables. So it's going to become x is equal to 2 to the power of f of x. And this is our inverse. So we're going to take this exponential form and turn it into logarithmic form. So I'm going to go log of my base, which is 2, and our answer is x is equal to our exponent. And actually right there already we can see that we've now proven that the inverse of this exponential form is actually the log of that form. Now I want to compare some stuff between these two graphs. So we're going to look at the domain, range, intercepts, and if they have an asymptote and where that occurs. So let's look at the exponential graph first. So that's our red graph here. Our domain looks like it can be any x value. So it goes from negative infinity all the way to positive infinity. Whereas our logarithmic graph, we actually can't go past 0. So 0 is our smallest graph. It's not, or sorry, smallest x. It's not included in our domain. And that goes all the way to positive infinity. So far not much to see. We can just see that it does in fact change when we do the inverse. Let's do the range then. So again, of our exponential graph, we can only go to 0. We don't include 0 in that. And it does go all the way to positive infinity. Uh-oh, here we go. We've got something happening here. These actually match between our logarithmic and our exponential. Just what was the domain has now become the range. So I bet you then that this domain is going to go here and that this is going to be negative infinity to infinity. They're just going to switch places. Well, let's check that out. So our exponential graph, well, yeah, our smallest y value we have, it goes all the way down to infinity or negative infinity. And then in a positive direction, it goes all the way to infinity as well. So yes, these have just swapped places or inversed. Let's look at the x-intercepts then. So on our exponential graph, actually we don't have one, so there's none. For our logarithmic graph, though, we do have an x-intercept, and it occurs at x equals 1. Again, not really much to see other than the fact that they are different. But let's take a look at the y-intercept then. Our exponential y-intercept, it happens at y equals 1. Oh, there we go. So there's the pattern. You can see what was before was x equals 1 is now y equals 1, which makes sense because we're taking our original equation, inversing it to become y comma x. So that actually makes sense, which probably leads me to guess that this none is probably going to go here as well. And we can check on the graph for that. So we go and look at our y-intercept, and yep, there is no y-intercept, so there's none there. Finally, our asymptote. So in our exponential graph, we have an asymptote at y equals 0. And based on this information right here that we're taking this inverse, without even looking at the graph, you can pretty much guess that it's now going to be x equals 0. And sure enough, we look at our graph, and we have an asymptote at x equals 0. There's one more thing we can do with this graph, and it's evaluate these 4 logarithms. So we want to know the value of log 2 of 0.5. Meaning, I'm going to go on my graph, and I'm going to find where our x value is 0.5, which happens right here. And we find out that our height at that point is -1. So not too bad. Okay, let's look at the next one. Here we have an x value of 1, so we go find where x is 1, and we find the height is 0. Height of x is 2, height of 1. And here we might have to do a bit of estimating. So we have where x is 7. Now our graph isn't perfect by any means. I'm going to say this is like 2.7-ish. If you're ever asked that on a test, within a couple decimal places is more than reasonable. Before we get into some examples that you might actually get on a test, I want to look at one more thing. And the question is, are y equals log base 1x, is that a logarithmic function? So we have to go and first turn this back into exponential form to actually think about this. So we have a base of 1 and an exponent of y and an x as our answer. So let's just think about this for 2 seconds. Let's just say, theoretically, I said x was 3. Is it possible for me to get 3 when I have a base of 1? No, there's no way I can. There's nothing I can put here in this y that will ever make this true. Like 1 to the power of 10, well, that's still 1. 1 to the power of a million is still 1. So this will never be true. So therefore the answer is no, that's not. Let's look at a couple more. So y equals log base 0 to the power of x. So same thing, let's put this in exponential form. So we have a base 0 and an exponent y, and it's equal to x. Again, let's pick a number for x. Let's say x was 5 this time. And we have a base 0. What exponent has to go on the 0 to make it equal to 5? Again, not possible. So that'll never happen. So the answer is no, that's not possible. Let's just try one more situation before we move on here. We have y log base negative 2 of x. So now we've got a negative base, and let's try that. So we got negative 2. This seems more plausible. Y, and then is equal to x in this case. So if I wanted a value, let's say x was 4. Is it possible to make this equal to 4? Well, yeah. Negative 2 squared is 4. So yay! Right? No. Here's a different number. What if I said negative 4? Is it possible to make negative 2 become negative 4 using an exponent here? Well, no, it doesn't matter. It doesn't matter if I put cubed or squared, or some people might say, oh, well, you just got to put a negative 2 there as our exponent. Well, no, that's something completely different, because it'll be 2 squared, which is 4, and you still have that negative, and that becomes a reciprocal. So no, there's no way to go from negative 2 to some exponent to negative 4. Now we have to remember what a function is. A function means that I can draw a line straight up and down, and there'll be no crossing over, and it should be continuous. Well, this would not be continuous. There's going to be a big gap in here. So then we have this rule where we only deal with bases that are greater than 1. We don't include 1 because of this first example right here. The other thing I want to go over, and we've touched this on a little bit, the calculator does not have different bases. So how could we graph this in our calculator? Well, what you would do is you have to use your change of base. So if I want to do log base 2x, I'm going to go log x and then log 2. And so that change of base, I can throw that into my calculator and it will graph it no problem.